Hello, greetings from Optima Design Automation. Welcome to DVCon Europe 2020 virtual tutorial on meeting ISO 26262 functional safety targets through static and dynamic fault analysis. Agenda, two parts to the agenda. The first part, who we are, quick automotive functional safety primer, overview of structural and hard error analysis, a demo of it. And the second part, we look into soft errors or transient faults, challenges and design issues, calculating the soft error impact, optimizing soft error safety mechanisms and design performance, a short demo of it, and finally ending the second part with Q&A. Optima Design Automation is the next generation automotive functional safety software provider. It is founded in 2014 at Nazareth, Israel. We have a portfolio of advanced solutions for complex safety and security challenges, a revolutionary technology for high-performance fault analysis. We are a well-funded organization with a core team of verification and safety experts. At the core of technology, we have FIE, Optima Fault Injection Engine, providing orders of magnitude faster than competing solutions. On top of it, we have Optima SEA, static analysis solution, Optima HE, hard error coverage, Optima SE, soft error mitigation, and Optima SEC, IC security verification. And myself, I'm Sesha Kumar, Director of Application Engineering. I have more than 25 years of experience, and the last 6 years I've been working in the area of functional safety. A quick functional safety primer. Automotive electronic safety standards define functional safety as absence of unreasonable risk due to hazards caused by malfunctioning behavior of electrical and electronic systems. A typical car today uses 300 processors, 50 plus complex electronic circuits, working in the functional area of airbag deployment, adaptive cruise control, automatic braking, driver alertness monitoring, accident recorder, battery management, digital turn signals, security systems, lane departure systems, parking assistance, etc. These are the very critical functional areas, making sure that driver and the passenger is safe inside the car. What are functional safety standards for each and every vertical of the industry? ISO 26262 defines automotive safety standards. It fits the entire process of verification and safety process into the V model, right from concept phase to product development at the system level, hardware level, software level, and to the production and operation. Let's consider a CPU typically used in an automotive system. ISO 26262 defines random faults that can occur during the operation. Safety mechanisms are used to correct these fault effects during the operation. Let's consider a fault occurs in RAM, which makes its output permanently 0 or 1. We call it as permanent fault or hard error. A safety mechanism used to correct or to detect that. Same is the case when a random fault occurs in the sensor control. Let's assume that it makes the output a temporary 0 or 1, which we call it as transient fault or soft error. A safety mechanism is provided in the way of hardened TMR flip-flops. ISO 26262 certification requires proof that high proportion of faults are protected. An ASIL level, automotive safety integrity level, is defined, and for ASIL D, 99% of the faults to be protected. We'll look into more detail of ASIL in the next slide. In essence, safety mechanism is to detect and mitigate or tolerate faults, or control or avoid failures to achieve a safe state of the system. Determining ISO 26262 level, it is defined as acceptable risk level for different automotive electronic applications. It primarily depends on three factors: severity, exposure, and controllability. Severity is how severe the injuries can be due to the incident. No injuries, light injuries, or life-threatening injuries. Exposure, how probable it is. Is it high probability or extremely low probable of this particular incident? Controllability, if this incident happens, is it very easy to control or it's completely uncontrollable? Based on different combinations, we can define different ASIL levels. At the highest level, the severity is life-threatening, exposure is very high probable, controllability is uncontrollable, which forms ASIL D, which is the highest requirement of any equipment. At the lowest level, there are no injuries, extremely low probability, and very easy to control. Just a simple quality management is sufficient. ISO26262 defines different fault types and probabilities of failure. Let's define each and every fault. Safe fault. This fault will not violate a safety goal. That's why the fault is called safe. Single point fault. These faults violate safety goal and there is no safety mechanism present to prevent that. These are dangerous and marked red. Residual fault. This also violates safety goal, but there is a safety mechanism present, but the safety mechanism is not able to cover these faults. This is a residual fault, residual within the design. It is dangerous. Multi-point fault is a combination of more than one fault. Alone, it cannot affect any safety goal, but in combination with others, it can affect. Multi-point faults are further segregated into detected, latent, and perceived. There are many fault metrics that must be established for critical fault types. We have fault metrics like fit rate, failure in time rate, SPFM, single point fault metric, LFM, latent fault metric. Fit is defined as failure in 1 billion hours of operation. Let's look at ASIL's some of the ratings. Fit rate should be less than 10, SPFM should be greater than 99%, LFM must be more than 90%. You can get more information in the provided link here. Let's look more into the fit rate. Fit rate, as we defined, in 1 billion hours of operation. ISO 26262 requires in the range of 100 fit rate. That means if a 100 fit rate vehicle, it has one failure in 1000 years of operation. Let's look at a different scenario. A company sells 1 million cars and 1 million cars, each one having 100 fit rate. So if you calculate the failure rate will be one failure in every 10 hours for 1 million vehicles, correct? So this is a real dangerous number. So we need to reduce fit rate. So we have to make sure that the fit rate is very low to make sure the automotive system is safe all the time. Let's consider again the CPU typically used in the car. How do we measure the fault coverage today? Fault simulation is used to measure the coverage by injecting faults and simulating repeatedly. Traditional fault simulators built for manufacturing tests, so they are not good for automotive. They are very, very slow. What is the time taken? Time taken will be a one gate level simulation multiplied by number of faults, because all the faults have to be simulated. Even if you do some operations to optimize the fault flares, it takes many, many weeks. Traditional fault simulation process is an iterative process and takes a lot of time. Let's have an overview of structural and hard error analysis. This is a zoomed in picture of an IC with transistors and connections in place. There can be a physical deformity or physical defect, damage for the transistor or the connections between transistors, and the wire can go touch a VDD or VSS, making itself permanently 0 or 1. We can model this kind of a scenario using stuck at faults, stuck at 0 or stuck at 1. Faults can be modeled even using bridge fault or any other faults. In this presentation, we are going to focus on stuck at faults. So stuck at faults can be on the primary gate's net output, and stuck at 0 or stuck at 1 are injected at the output net of a primary gate. It can be pin based as well. The primary gate's input and output pins are injected with stuck at 0 or stuck at 1 faults. In the current day scenario, there are multi-million gate IC designs that are possible. There will be millions of faults that need to be simulated. So we need to optimize this fault list to expedite the process of fault simulation. Fault list has to be pruned. That means you need to figure out what are the safe faults. In the OSP, Optima safety platform, it will be segregated as safety invisible and safety visible. We'll look into this in more detail in the coming slides. Fault collapsing, find out equivalent faults that can be collapsed and only remaining faults can be simulated. Constant analysis can be done to make sure that all the configuration registers or any other constants in the design can be marked as safe. Let's look into the fault collapsing. Look at the final AND gate stage. The output stuck at 0 and input stuck at 0, both are equivalent. So these are called equivalent faults. You can collapse one of them and use the remaining ones. Same is the case with the OR gate, where the output is stuck at 1 and input also is stuck at 1. These are equivalent. You can collapse one of them and try to use the remaining faults. So these collapsed faults are counted for the calculations but not used for simulations. In essence, ISO26262 requirement simplified as for hard errors, semiconductor needs to have a safety mechanism that can detect hard errors within the budgeted interval from the time they happen. So the safety mechanism needs to be running continuously while the device is in operation. Safety mechanism needs to have a minimum diagnostic coverage. It needs to cover not less than n% of possible faults. And different ASIL levels have different n values. For example, ASIL D will have 99% of the faults to be covered by the safety mechanism. This depicts a flowchart which is iterative in nature for measuring safety mechanisms coverage process. You write the tests, run the fault simulation. Is your coverage metrics meeting your requirements? Coverage results? No. Develop a method to improve the coverage. Fine-tune the test, run the fault simulation. If you meet the coverage requirement for the faults, done. This is an iterative process. There are a couple of challenges. The challenge number 1, it takes a long time to run fault simulation. Challenge number 2, the coverage holes are very hard to detect. Let's consider a realistic example of Lockstep safety mechanism methodology. E10 GMAC is working as a master here with inputs and outputs. If any fault occurs in E10 GMAC, will actually violate the safety goal at the output. As per the safety mechanism, to tolerate or to detect, we are going to put a shadow E10 GMAC in the form of a lockstep working in the same clock cycle or clock cycle away. And the outputs are compared, and the signals that come out of the compare outputs is the detection strobe. So we call the safety goal violators as failure strobes and the detection points as the detection strobe. How do we set up this design for this static analysis? Let's look at the safety setup and static analysis of the design under safety assessment. So we should define detection strobes and the failure strobes and run the static analysis. So what the static analysis can do is form a COI, cone of influence. This means that all these faults can affect the failure strobe and also form a COI for the detection strobe. So all these faults can be detected. And there are some intersection faults that can occur between these two COIs. Let's try to understand the faults in each area. If a fault is there in the red area, what do we call this? This is unsafe because it is hitting the failure strobe. It is invisible because it's not going to the detection strobe. So these are the faults important for the user to take care, because these faults don't have any safety mechanism. Otherwise, it would have ended up in a detection strobe. Since no detection strobe is available for this, the designer need to focus on these faults to put a safety mechanism in place for this to be detectable. And next is the safe invisible. These are safe because they're not ending up in any failure strobe. They're invisible because there's no end point of the detection. So we can call them as safe invisible. Safe visible, these are safe because they're not going to the failure strobe. They are visible because they're ending up at detection strobe. These are safe because it's not affecting any failure strobe. And what is the intersection? Intersection, we call it as unsafe visible. They're unsafe because ending up at failure strobe, and they're detectable or visible because they're ending up at detection strobe. So these are the important information that we can get from any structural or static analysis. One is UI, which need to be taken care to provide a safety mechanism. UV, which are potentially detectable, and you need to take further action on the unsafe visible faults. There can be complex safety setups. single or multiple failure modes. The safety setup can be freely mixed and matched. It may include a single failure mode and its safety mechanism, multiple failure modes and their safety mechanisms, and different combinations of this. So your methodology should cater for doing mix and match of different failure modes and safety mechanisms. So by doing static analysis using OSP, just by giving the RTL gate level design and a simple safety setup in the form of failure strobes and detection strobes, we're going to have immense valuable information in the form of UI, where you need to take care of them by providing a safety mechanism, structural debug, early identification of major issues. And you can take these numbers into FMEDA parameters and then start working on FMEDA metrics. And you also have an optimized fault list because collapsing and fault pruning happens in this stage. ASIL C and D, the initial phase of more extensive analysis is required. For ASIL A and B, this might be all that is required, right? So you don't need to go further to any other stage of functional safety verification, depending on the result. So how do we map the structural analysis result we got in the form of different fault statuses, SI, SV, UV, and UI, and mapping them to the ISO26262 defined faults? So safe faults can directly map to the safe invisible. A single point fault which doesn't have a safety mechanism in place, that means these faults end up only at the failure strobe, not at the detection strobe. They are straight into UI. Residual fault. These are faults which violate safety goal. There is a safety mechanism present, that means they are visible, but the safety mechanism is not covering. That means that when you simulate UV, if the fault is not detected at the detection points, we call them as residual fault. So we need to simulate the UV to find. So we are still at structural analysis. So we have to take the structural analysis result to the fault simulation. A multi-point fault detected. This is a combination of more than one fault that violates the safety goal. You need to simulate UV further to find out both residual and multi-point detected. Latent fault, you need to simulate SV because these are visible but potentially visible, but we don't know it's really detectable or not. You have to simulate using hard error analysis engine. So now for hard error analysis, we have the inputs from the structural analysis. The structural analysis gives us SI, SV, UV, and UI fault statuses with detection strobes and failure strobes. So the beauty of OSP is that it's a single setup and we can go and use different engines. HE hard error analysis requires workload that is in the form of a stimulus, VCD. And by taking VCD, the fault simulation happens and the UV faults will be able to get detected and mark them as unsafe visible detected. And they may not be able to detect it at the detection point. So we call it as a residual fault. So again, this is in red, dangerous. Designer need to take care of it. So the initial static analysis gave an information of unsafe invisible where there is no safety mechanism. A UVR, there is a safety mechanism, but safety mechanism is not covering all the faults. UVR, residual faults. So how do we map this to the entire gamut of ISO26262 fault statuses? After running HE, the whole fault statuses can be mapped onto ISO26262 definitions. SI, SV, UVD, and not detected. So all the faults are depicted here. I'm not going through the complete flow chart, but this exactly maps the whole fault list from SEA HE analysis to the ISO26262 fault types. I just want to show the demo of structural analysis and hard error analysis. So the safety setup is very, very simple, as I explained in the slides. We just have to analyze the design. So I picked up the same E10GMAC here, and we're just analyzing the files, Verilog files. So here there is a read lib. That means whatever the library cells that are modeled here can be read as a library. Then you have all the options of including directories and choosing the format, and choosing all the files of the design. And then elaborate your design. So this elaborates your top level. You can choose the top if it is a multi-top design. And the safety setup is very, very simple. The first is to define the detection probes. So when we call detection probes, that means the error is detected. So error is detected at the safety mechanism, right? So define the safety mechanism's outputs or any signal inside the design as a safety mechanism output, meaning detection strobe. That's where the error is detected. So the safety setup is also defined on some of the receiver and transmitter FIFOs, like so data FIFO, and the hold FIFO and the stats FIFO, right? And both transmitter and receiver. So once we define the safety setup for the fault detection, which we call it as detection strobe, then what we are trying to do here is define the outputs of E10G MAC completely as a failure strobe, right? So that's what we defined in the picture as well. So the failure happens when there is a fault at the outputs. So these are all fault strobes. So we can define just dash default and it takes all the outputs as a failure strobe. Static analysis is run by run assay, and what it does is to analyze COIs and then find out what are the intersection of the faults, and then try to analyze what are the faults that have to be looked at from the initial analysis. Then we load the trace. This is important because we need to simulate some of the faults, which we are going to simulate the UV faults. The command is trace, and you can set up the start time from which the simulation has to be read, and the end time will be default end of the simulation, or you can specify the end simulation time as well. And here in this file, for the demo sake, what I have done is I'm running the hard error analysis as well with some faults randomly chosen for stuck at 1 as well as stuck at 0. So for stuck at 1, I have chosen some 300 faults, and for stuck at 0 also I have chosen some 300 faults, and I'm going to run this. So I'm going to run this in a tickle mode, and let's see what happens. And end of the demo, I'll also show you how the full list of the faults look like. So the command is OSP, that is Optima Safety Platform, and you can source it. And you can also define a log there. So this is blazing fast for this small design. So you can see at the right side, you can see the triangles where the static analysis or structural analysis is being done. Now it is loading the trace. So while it loads the trace, so you can just view the graphic user interface. So the first window here on the left side is kind of a safety setup dashboards. You can have multiple safety setups. As we said, you can have multiple setups. You can merge them and try to analyze which safety mechanism is good for which detection, which failure mode. And on the below, you can see the hierarchy dashboard, and you also can see the nodes dashboard. On the right side, you see the triangles, and you can also see the fault table where all the faults are listed here with the status. And below the safety visualizer dashboard, you have the table which tells what are the total number of faults and their categories like SI, UV, and number of faults covered, number of gates, flops, etc. What do we get from this? Static analysis, right? So very initial look, it says that UI, unsafe, invisible, or 220. So these are dangerous, right? Because UI is defined as faults that don't have safety mechanism. So user has to worry about these 220 faults and then make sure that there is a safety mechanism present in the design. And simultaneously, UV was decided at 31,496, but having run these 300 faults, those 300 stuck at 1 and 300 stuck at 0, so around 600 faults we have run. And tool has also determined there are some collapsible faults. As we talked about, you have to minimize the fault list by collapsing and pruning and constant analysis. So what we have done here is we have just used the collapsing information. Let me show you that. So here engine will run 276 faults, right? But whereas we have given around 300 faults. So total given number of faults is 300, number of faults after collapsing is 76. That means remaining faults are collapsed, right? And 276 is run. Out of 276, this is the status. Of course, there are another 300 we have run for Stuttgart 1 as well. So out of which 600 faults, there are some collapsed and only 226 are covered, right? In this way, a simple way of setting the safety setup with simple fault detection strobes and performing the static analysis or structural analysis and then running the trace. It's very simple to run the Optima safety platform. So where you have just set up the safety with respect to the fault detection strobes and run the SA. SA will determine the UV, SI, SV and SI. And HE will run the defined faults, or by default it will run the UV faults and give us the coverage. So this is the fastest way to get to the FMEDA mapped fault list and then try to analyze your design based on the outputs, right? So like, for example, we said the UI faults have to be taken care first, and then how many detected, how many not detected. If they are not detected, why they are residual. So before talking more about the residual faults, I want to show the complete fault list which we have run before this demo. So all the 31,496 faults have been run, and for this workload, this VCD has given us 78% of the total faults, and some of them are still UI. So this is where user still has to take care of putting a safety mechanism in place and making sure that they fall into other categories than UI. So this is the demo, which is very simple and effective of Optima safety platform. Thank you. And let's look at challenges dealing with the transient faults or soft errors. What are they? Transient faults, generally we call them as SEU or SET, single event upset or single event transient. These are bit flips caused mostly by cosmic rays, mostly by radiation from the sun. Where do they hit and how do we protect them? So it can hit memory bits, and we have a very well defined protection mechanism like bit de-alignment and ECC, etc. It can hit the gates, but it has very low probability to hit exactly at the right time to get a wrong value latched. And most of the experts don't consider this. It can hit flip-flops, bit flips in a single flop, and we'll see what can be done with these flops in the next slides. We can actually use the TMR, which is popularly used in many designs. TMR is triple module redundancy with majority voter, 3 flip-flops instantiated, and a majority voter selects the right value. And DMR, double module redundancy with the charging element, also is one of the popular models to be used for flip-flop hardening. We can also employ system redundancy to correct soft errors. Like we did for the single flop, we can use DMR, double module redundancy. A module is duplicated. In this, you can actually detect single fault, no correction capability, and the cost is increasing by 2x. TMR, single fault correction, dual fault detection, the cost is increased by 3x. All the modules are triplicated. And TMR of TMRs compares 3 implementations, protects against design errors too, and the cost increased by 9x. All these designs are very expensive. Let's look into the flip-flop hardening examples. So if you use a lockstep mechanism at the unit level of the flop, still 70% more silicon has to be spent. Let's look at flip-flop hardening examples. At unit level, you can use lockstep mechanism. The cost is 70% more silicon. Hardening all the flops, 30% more silicon, selective flip-flop hardening. This is the technique mostly used in the current day scenarios. Using older nodes, we cannot go back. Using special red hard silicon technologies, these are very, very expensive. So let's look at selective flip-flop hardening. If we harden flip-flop by TMR and DMR techniques, the extra area penalty is still more, but we may reduce the fit rate down to 0 or almost down to 95%. Let's look at the selective hardening at the flip-flop level. More detail. Hardened flip-flops can eliminate transient faults only a small portion of flops require hardening to eliminate faults. We should calculate something called AVF, Architectural Vulnerability Factor, to calculate the fit rates. Fit rate can be optimized using iterative fault simulations while swapping unhardened flop with the hardened flop. And today it requires many months of fault simulation for analysis. What is AVF? So AVF is simply the probability that when a transient fault hits a flop, it reaches the safety goal. Often these flip-flops outputs are masked through natural logic masking in the signal path. Flip-flops logically masked most of the times have very low AVF. Can we leverage this by calculating AVF? Yes, a lot of industry leaders do calculate AVF, TVF, and PVF vulnerability factors to measure vulnerability of hardware to the soft errors. Here we present Intel's paper in IQPC 2019. How do we calculate a reliable AVF? Multiple soft error fault simulations are performed for each flop. Each SE is injected at different time cycle in the simulation. Optima recommends 50 to 100 faults per flop. Each fault simulation can end with a propagated fault. That means a fault propagates to a safety critical node. A fault is dissipated. That means it disappears in the course of simulation. End of trace. The fault sim has reached the end of simulation without any of the results above. So the AVF is calculated number of propagated faults over total fault simulations executed. How do we use that? Let's assume that you don't have AVF calculations. That means fit rate is calculated with the number of flip-flops multiplied by the fit rate of each individual flip-flop, unhardened. If it meets the requirement, well and good, we can go ahead with the design. If not, calculate the AVF for each flop. Fit rate number is a summation of AVF multiplied by the fit rate of the unhardened device. Because you calculated AVF, so now fit rate is more accurately calculated. What if you have hardened the design, some of the flops, right? With selective hardening of the M flops, you'll have the fit rate as a summation of two numbers. The first component is the hardened flip-flops fit rate, which is nothing but AVF multiplied by the hardened flip-flops fit rate. Hardened flip-flop fit rate is almost close to zero, so this first term is mostly zero. And the second term is very low. So by hardening the flip-flops, you are actually lowering the fit rate of the chip. So the calculation of AVF can take many compute resources. Calculating AVF involves performing fault simulations on all the flops. Each flop needs to be fault simulated 50 to 100 times. Historically, this has been a very lengthy process. You need a new approach to fault simulation and a platform to manage large number of faults. To put it in perspective, you have to measure the fit rate using AVF calculation. Did you meet the fit rate? If not, perform hardening on selected flops. Calculate post-hardened fit rate. Did you meet? Otherwise, go back. So this is an iterative process. Hardening less than 5% of the flops will actually get you close to the fit rate of zero, meeting ASIL requirements. So to have an accurate SE analysis and calculate AVF based fit rate, you need a fast simulator as well as a dedicated platform. Thank you. For any queries, please contact info@optimada.com. Let's look at SE demo. Thank you.
Load the design using Tickle, and OSP safety platform would have already marked some of the nets as critical. You can browse through the database and mark yourself some nets critical. This can be done using GUI or using Tickle interface. Once the nets are marked, you can run the prep engine, and this will actually do the COI analysis and prepare the database for all the critical flip-flops. In this run, we're going to run 20 faults per flop. The Optima safety platform can perform soft error injection and also create the simulation VCDs. This can be used only for debugging, otherwise there is no analysis needed graphically. Now you can see the third row, which is the AVF, is populated with some numbers. This will indicate the vulnerability factor for the flops, and overall the top 5% of the flops are selected for the hardening. In this run, we're going to see only 3.5% of the flops are selected in the whole design. Yeah, the run is finished, and you can see only around 3.5% of the flops are selected for the hardening. In this way, Optima safety platform provides an easy way to analyze the soft error for various flops and to recognize what are the vulnerability factors for different flops and select the top 5% of the flops for the hardening.
Thank you. For any queries, please contact info@optimada.com.